here that talk about the Jacob Palace that passed away in the beginning of May. It's very difficult to enter in this room. When I entered the first day, I looked to the auditorium. I felt this is different, but this is because this huge screen. But well, Jaco Trieste is part of the life of many of us. Well, we participate in many meetings here. Jaco started to organize meetings in Trieste with Sinai, and Pedro Seaman first, and after Seaman, he organized several meetings with Sinai and Jocos. Here is a photo of Jaco in the cafeteria of ICTP. Perhaps you, I don't know, it is machines, I guess that they are still there. We have fantastic days as ICTP. Here, well, as I told you, Jaco started to organize the meetings with Seaman, but at some time he started to organize the meetings with Jean-Christophe Jocos, Jacob Sinai, and Marcelo Viana. This is a photo of the four organizers. This was, you think about this now, they organized 3 weeks conference. The first 2 were schools. I guess that Sylvain gave a course. Perhaps other people, I forgot no, I don't know, si Masato, the people, but many of us, I didn't, gave talk here. Many of us also participate in this conference. This is a photo that I want to show you because many of you talked about, let me show, about Ricardo Mañé here and Artur Lopez. Here in the photo you can see Jaco, Floris Takens, Patrick Bonquer, that he was a student of Frédéric Dumotier at past one postdoc here in Rio. You can see also Paulo Sad and Carlos Gutierrez. Unfortunately, many people in this photo is not with us anymore. Well, let me say some photos. Perhaps you can see the evolution of these schools. This is, well, Alberto this morning mentioned that Jaco started organizing the conference in the 80s. I think that this is one of the 2 first schools. Perhaps you can see many people there. Let me now show another 2 photos. The more recent, well, I think that Jaco, I don't know, Cece, perhaps you can help me. The last school organized by Jaco was in 2000 something. I don't remember. It's impossible to put all the photos. But when Jaco passed away, the Chinese mathematician Lang Wen sent his email to me. Sorry. Well, he emphasized one of the main properties of Jaco. I see many Chinese mathematicians here, but I think that the things that Lang wrote about the Chinese community is also valid for people from Iran and other countries. And then I see that I need to proceed. Well, this is the photo of the last edition, and then I will let the photo here. You can identify Stefano Lusato is there, among other people. And then I have here a box of cartucci that is a prize for the people under 60. The cartucci are very hard for people beyond 60s. And then the people that identify more participants in this photo will get a cartucci as a gift at the end of my talk. Well, now let me recover a little and go to the math. I need my glasses. Okay. Okay, then I can do something. Okay, I pass here, and then this is the main inspiration for my talk is this descent made by one of my co-authors, Catherine Gelfer. That is the inspiration for this talk. And then I will move back, and then we can discuss the photo. Well, thank you, Jairo. The setting of my talk is I am considering diffeomorphisms that have a partially hyperbolic splitting with 3 directions. As you know, this is uniformly contracting. This is uniformly expanding. And in my talk, this is a center manifold that is one-dimensional, at is in between. Okay? Okay. Then the system that we are considering, you have here the ambient manifold. You have, say, 2 parts of the manifold. In this part, well, you have points where the central bundle is contracting, and there are other points where the central bundle is expanding. And then, well, you have transitions between these 2 regimes, the contracting regime and the expanding regime, and you are interested in the resulting dynamics. And well, we are interested in systems which are transitive. I will provide more details later. Okay? Well, let me make two comments. The fact that here you have a center bundle, I am not assuming any integrability of the center bundle, only I assuming the existence of the bundle. This implies that when you consider the oscillated splitting, this bundle is one of the bundles of the oscillated composition, and then you always have a very well defined central Lyapunov exponent. And the situation that we are considering, due to the fact that we have here a part that is contracting and another part that is expanding, is that we have measures, well, ergodic measures, so that the exponent is positive for some measure and other measure that have negative exponents. And then, well, here in this talk, most of the people was interested in hyperbolic things. I am interested in non-hyperbolic things. And then, well, if you have measures, as well, I don't know, you are very picky, but assume that you are here, you have a periodic point that is with the central exponent is negative, and another point whose central exponent is positive. Then you have the measure supported in one point and the measure supported on the other point. But you know, we will consider systems that have plenty of measures with positive exponents, plenty of measures with negative exponents, and the point that we are interested is in the measure we have 0 exponent. And also, due to the nature of the system that we have uniformly contracting and uniformly expanding direction, the hyperbolicity and the type of hyperbolicity is given what happens in the central direction, because the other exponents associated to the directions which are contained in ES or the directions that are contained in U are either negative or positive, okay? I don't know if, okay, let me just say 2 things which are important due to this fact. The fact is, is an important fact, property that follows from the constants, is now if you take a sequence of measures that convert in the weak star topology to some measure, suppose that you have something that is ergodic. I will discuss this later. Then these exponents and these exponents are given by integrals. You are integrating in the central bundle. And then what happens is that we have weak star convergence, and we are considering Lyapunov exponents which are given by integrals. You have this property. In particular, if you jump to to dimension 2, this property goes to the, is not valid anymore. And then, well, another thing that unfortunately, I don't have many time to explain, but is a very important ingredient that is a result by Kiveniat and Watka, that they introduce a metric that they don't introduce this metric existed. I will say some words about this Feldman-Katok metric. I promise to say something, but the Feldman-Katok metric implies, in our context, that if you have a sequence of measures that converge in the Feldman-Katok to a measure mu, Feldman-Katok convergence implies also convergence in the weak star topology, and this implies that the entropies converge to the entropy of the measure. Let me just advertise. Well, that's okay. You are completely right, but I put together your result in this central. Okay. Well, let me just call the attention that when we discovered this method, we were extremely happy, and this is extremely useful. Ask Dominique for more information. Okay. Well, one second, please. As I am telling you, I am interested in settings where you have ergodic measures. Well, the goal ergodic measure. Removing ergodicity makes the problem trivial with exponent equal to 0. And then we are interested in problems about the entropy and so on. Okay? Well, when we study this class of problems, the first problem that probably many of you found when doing your activities is the limit of an ergodic sequence of measures. Ergodic?
Sorry, Lorenzo, I'm sorry to be picky.
Oh, no, my God.
The goal is what? The existence or what?
Study ergodic measure with 0 and Lyapunov exponent. We will prove the existence. Wait seconds. Be patient. Okay? Thank you, Stefano. Well, we will consider a case that we have a lot of measures. We have 0 entropy with positive entropy, many results. But I was trying to tell you a history, but apparently it's not that simple. Okay, well, if you try you have a sequence of ergodic measures and try to find if the limit is ergodic, the answer to this is no. And then, well, there are, this is a slide just that you be nervous, is, well, if you don't read this slide, but this is the kind of things that you need to do if you want to prove that the limit of an ergodic measure is ergodic. Okay, you need to, well, it's not very surprising because you need to compare, to estimate the average of potential, that is the common stuff. And this is a criterion that, well, appear, the first time that I saw this criterion was on a paper by Gorodetsky, Ilyachenko, Kleskin, and Navsky. We discovered thereafter that there is another paper by Wise that is a slightly different formulation, and this is the formulation that is a slightly variation of the previous paper that we wrote in our paper with Michael Rams and Catherine Gelfer. But you need to suffer a little if you want to prove ergodicity. And then, sorry. No. And that is quite complicated. But there is the beginning of the history. It's a paper of 2005, and I guess that is, for me, is also a conference, a beyond conference. I think that is the conference where I met Anton Gorodetsky and we start working. It's a paper by this, let me just call Gorodetsky and Co. of 2005, where they construct, there is a natural question, there are systems that have non-hyperbolic ergodic measures, really, or with some paired system. And then the first example that these people do, that is, we work on this in many variations since many years, is the following. You take the shift space times the circle. You have here the shift, and in the circle you have two maps. I am doing something that is wrong, but I know that you are not very picky then. You have here an irrational notation, and then you have a Morse-Smale map. Say the north is attracting and the south is repelling. And then, well, you consider the map that in the first, you take here a point alpha x. You consider the shift in the first coordinate, and here you put f al naught of x. Okay? This means that you have here a regime where the centrally upon exponent, you have here a regime that is, we have, or the contrary, sorry, this is contracting, this is expanding, but then using the rational rotation, you can jump from one system to the other, and then, well, you can produce, mingle the attracting and the periodic behavior, and then they prove that with this hypothesis, the hypotheses are more general, but I want to explain you. This system that let me call F, well, of course, in this system, you can only talk about the Lyapunov exponent corresponding to the central direction. Well, this split, this manifold, you have measured such that the exponent of the measure is 0, and this measure is ergodic. Probably next week, Jiang and Zhang will give an extremely interesting talk about something about, non-hyperbolic measure in conservative system, and certainly I suppose that he will revisit this construction with more details. But let me more or less explain what is the idea of this construction. It's something that we now call shadowing and tailing. That is the following. You start with a periodic measure, a periodic point.
Sorry, but this ergodic measure is like
no, this measure is very bad. Don't expect absolute continuities about this measure.
this measure is not an atomic measure.
Not atomic. Wait 2 seconds, because, well, you start with a periodic orbit that we call the periodic orbit of generation 0. And then you get a second orbit that shadowed or mimics the first orbit during a very long period, and then have a tail. Okay? This is the second periodic point. And then what you do, or what they did, is that you get another measure that mimics now and have another tail, and so on and so far. And then what these people prove is if you take this, the average, the shadowing time and the tiling time in a good proportion, then the limit of these methods, you have these methods, which are periodic, converge to some ergodic method, And in the case that they have, well, these tails are done to visit an expanding region, and then prove, in addition, that this method has 0 Lyapunov exponent. Well, this is a very 2005, and what Dominique Watka proved is that in this convergence is, and now exactly what, this convergence is indeed in the Feldman-Katok convergence, as using the result by Dominique. Well, now we can use the result of Dominique. We know that this method has 0 entropy. Okay? These methods, I remember that I gave once a talk in Paris, and Jérôme Bouzy was there. Jérôme Bouzy asked me, Lorenzo, what is the entropy of this method? And I said, I don't know. And Jérôme told me, well, Lorenzo, this is a kind of adding machine that is not exactly like this. And then, well, after many years, Dominique and Watka proved that indeed this method has positive entropy. 0 entropy, sorry, excuse me. Okay.
We're listening.
Sorry?
We're listening.
Okay, yes, thank you, great, great. Okay, well then, in collaboration with okay, good, with Christian and Jairo Bocchi, we prove the following. If you have a diffeo in the topology C1 that is robustly transitive, robustly transitive means that the diffeo is transitive and every perturbation is also transitive, and it's also robustly non-hyperbolic. This means that the diffeo is not hyperbolic. And then, in this case, we prove that open and densely there are ergodic methods with exponent equal to 0 and positive entropy. Okay, this is what I got. And this morning, when I was discussing my talk with Catherine, she told me, Lorenzo, you will not be able to explain the next page, and she is right. And then I need to jump a little. And then, well, once that we know that we have measured with positive entropy, we can start to make questions about that measure, okay? Yes. You don't need to have one-dimensional center, but at the end of the day, you pay the attention to some part of the dynamics that is partially hyperbolic with one-dimensional center. You have some part of the dynamics where you have some hyperbolic set, where you have, locally, you have a central direction that you cannot extend to the whole set. But this is indeed, well, this is not assumed, but this is a one-dimensional EC. If you want to use the method, you need to use implicitly is there, because also is not explicit. And then now, after this perhaps too long introduction, let me go to my results. I am very happy that, you know, when you write a paper, you need a lot of energy to convince the referee that your results are not very specific. You say, this result holds for an open or dense. But anyway, referees insist, no, this is very specific. Now, I am very lucky, because first Emi in his talk explained that minimal foliations are very interesting. And Meisan explained you that blenders are great. Then I don't need to convince, I hope, anybody. And then let me now explain the setting. What we assume, well, first still we have this partial hyperbolicity with 3 bundles. We assume minimal foliations. we have these foliations which are minimal, and we assume that there are a pair of blender. Well, you know, there are many people that talk about blenders, but we need blender that has some internal structure, and that is something that we call blender horseshoes. And these are the two hypotheses that we assume. Okay, let me just say that there are many examples. For instance, if you only consider dimension 3, this condition is open and dense for skew products. I am assuming over S1. It's open also and dense for flow type systems. Is also, well, I am essentially repeating the list of examples in the talk of EMI. Some DA, this is due to a work by Hannah Rodriguez-Kerr, Raul Lures, and Yaganja, and also some anomalous examples where you have transitivity and you don't have integrability of the central bond. Then I just want to tell you that there are many, many examples with this property, and indeed, well, when you are in this kind of configuration, the blenders of the two types of hyperbolicity appear very naturally, and then to prove the minimality of the foliations, essentially what you do is to use this pair of blenders, okay? Okay. Well, I wanted to tell two words about blenders here. Why? Because different people use blenders in different ways. And let me explain how we use blenders or blender horseshoes. Well, philosophically, and you can see in this example, when you are close to the attracting point, using this is the diffeo F0, and this is the diffeo F1. If you are close to the north, if you repeat F0, you can remain in the contracting point as long as you want. But if you are in the expanding point, if you start repeating F0, at some moment you go to the north, and then you start losing the contraction. And then what allows us, the blenders, to do is the following, where I am doing a two-dimensional representation of the blender. Okay, I am killing the stable direction. This is the central, and this is the unstable. What happens when you are in a blender is that you have a collection of disks here. Well, I am assuming that I have a strong and stable foliation. You can simply take the disks in the foliation because they are invariant. If you take any disk here, you know that there is a part of the disk that when you consider, let me assume that you have the blender for F, you get another disk, this is delta, another disk of the blender. And then that means that if you have a disk that intersects the blender region, you can fix it an arbitrary number n, you can select a point or a small disk that stay all the time inside the blender, and as a consequence, you are expanding in the central direction. Indeed, what we have is a little more, because we can say that if we have a sufficiently small strip foliated by this disk, depending on the size of the strip, I can guarantee that this strip produce new strip. Well, of course, you need to pay attention, but if the strip increase, and in some moment you are outside the blender, but you have a kind of uniform result considering strip. Okay, this is the way that we use blenders. And now I think that I will start stating results. Well, the first result that I want to prove is that in the setting, we have the following. Every non-hyperbolic measure, a non-hyperbolic measure for me is ergodic and has exponent equal to 0. If you take any ergodic non-hyperbolic measure, is the limit and I need to be a little more precise. This limit is in the weak star topology and also in entropy of a sequence of measures such that, well, this measure you have to sequence. The measure corresponding to plus surprisingly have positive exponent, and the measure associated to minus you have negative exponent. That is, you have a figure like this. Well, this is a completely fake figure, but it's just a symbolic figure. You take here any measure here. Here are the measures with positive exponent. Here are the measures with negative exponent. And then you have a sequence of measures from both sides that accumulate to mu. Well, this is a result that was proved independently by Yang and Zhang, and in collaboration with Gelfer and meu Deus, Santiago. I also call Bruno, and then Santiago went to the hell. This is the result that we have. Just to, well, okay. Okay, let me, before, I forgot to say something interesting. That, well, in this setting, let me call the setting box. Use a philosophical comment. When you start to talking about non-hyperbolicity of a system, and you can think of this a little from the ergodic point of view, you have many possibilities. What is a non-hyperbolic system? Well, there are three cases, at least, that we found more interesting. The first setting is that you have ergodic mu with exponent equal to 0. Second, you may have that there are points with Lyapunov exponent of the point equal to 0. Of course, 1 implies 2. And third, that you have a sequence mu k, ergodic, such that the Lyapunov exponent of these measures goes to 0. I think that if you have a system that satisfies one of these three conditions, we can refer to the system honestly as a non-hyperbolic system, and then in our setting, all holds. Okay? You have simultaneously the three characterization, or I don't know, whatever, of the non-hyperbolic behavior. And then, well, now let me to state the first result. For this, I need, well, we need to, well, now we know that there are non-hyperbolic measures. This is due to this result by, well, this is not exactly that result, but it's a consequence of the result. I don't want to be picky, okay? Then we know that there are hyperbolic measures, and then we want to know how big is the hyperbolicity, and then we need to quantify Janssen.
That's this theorem.
This theory was proved independently by Janssen and a paper with Gelfers and Santoro. I don't know if this has 2000 something, 2000, say 20, for instance, or around. I don't remember it. Before pandemic. BP. Okay. Okay. And then we want to quantify no hyperbolicity. And then, well, to quantify no hyperbolicity, you take a number alpha, you consider the level set L of alpha. What is this level? Is the set of points that the central exponent of this point is alpha. Okay? And then you can consider the topological entropy. Well, attention, because you need to be careful, because this set is an awful set. Okay? You can talk about the topological entropy of this system. And then the theorem, well, let me write here. The theorem is joined with Catherine and Ji-Hwan Zhang. First, well, and now, well, one, there are numbers alpha min of alpha max, so that for every alpha in the open interval, we have that this set is non-empty and has topological entropy bigger than 0. Well, let me say several things. Here, really, the interesting part is for alpha equal to 0. Because for alpha different from 0, you are in a partially hyperbolic system, you have horseshoes, and then it's relatively simple. And then another thing is deal with the boundary alpha min of alpha max. Indeed, these are the possible Lyapunov exponents are this interval. Okay, you have that any interval, any Lyapunov exponent is in this interval, but deal with the boundaries of this interval is a problem of different nature. You can think that this fall in the field of ergodic optimization or something like this, but it's a different kind of problem because we don't have tools. Well, this I said you that the important part is for alpha equals 0, but you know for alpha equals 0 is in principle essentially we repeat this, and well. Well, because you know you have minimal foliation, you have blenders, and then you have a hyperbolic measure. One that you have a hyperbolic measure using the results of Sylvain or Catherine, you have some horseshoe that approach that measure, and then it's more or less relatively simple. It's relatively, you can, well, it's not the, believe me, it's not the complicated part. And indeed, what we prove, that is, I think, that is the interesting thing, is you have this map. This map is this map is like this, okay? Indeed. Okay, I am going in the wrong direction. No, completely wrong direction, my God. These are some possible shapes of the entropy map. You have two concave maps. Here is 0, here is alpha max, here is alpha min. And then the entropy map is continuous and concave in the zero part, in the negative part, and is also continuous and concave in the positive part, and they glue nicely in the zero value. And then, well, here there is a kind of zoo of possible configuration of the entropy map. For instance, here is what happened, the first figure is what happened when you have a skew product, because in that case, well, there are many people that work on this. You have that the measure of maximal entropy appear in pairs. You may, for instance, we don't know that this is possible, that is, maybe we have a plateau in the maximum. We don't know if the maximum in one side is less than the maximum in the other side. For instance, this is what happens perhaps in the DA systems, or perhaps in the DA system happen this, I don't know. These two figures are the candidates for the DA system. We don't know if the measure with maximal entropy is the measure with zero exponent. In principle, we don't believe this. Well, I send the title of my talk, and then, well, I prepared my talk, and then I started to attend the conference, and then I discovered that I was somewhat in the wrong place, because here the people are much more interested in cocycles. But let me tell you that we have a paper with Michael Rams, that we have similar results, similar results, no, because in the case of cocycles, you cannot have we consider elliptic cocycles. In SL2R, okay, and open and densely among the elliptic cocycles, we have, I think, Catherine, correct me, the first figure. No, the cocycle you only have one part, because only have one diaphragm response, the other is the inverse. But for instance, in the case of elliptic cocycles, you don't have plateaus, because, well, you need to use this, but I just want to emphasize that we have results about elliptic cocycles in a parallel way. Well, indeed, in the result with Jagansan and Catherine, we prove the following. Well, this more or less, well, for instance, let me use, I think that my time is 6 minutes is evaporating. I will go to the last result, because otherwise I would like to say that we also get a description of this set. Okay, we have a good description of this set. Okay, and now, as I have only 6 minutes, I need to go to the next slide. That is the title of my talk. Is about flexibility. Well, I think that, well, flexibility was a notion introduced by Katok, I guess, and then Federico and Janeiro wrote a paper with Katok about flexibility, but what Katok has in mind, or these people made, was a results mostly about Lyapunov exponents. But you can reformulate this kind of results for other quantities. For instance, you can...
Actually, the first flexibility he asked was to it was about entropies.
Well, thank you so much, because I didn't know that. Good. It's a pity that it's not written, because... Well, I was trying to mention also Etsenko, but I didn't remember her name. But then we thought about flexibility, and what we proved jointly with Michael Rams and Ji Hua Sang. Well, you can do this in in any level, but let me use to state in the 0 level, and then I will stop. Is the following. Well, let me just say that there is some previous results of Tian, Zhang, and well, I need to check my notes, but there is a poster it was a poster in the corridor about, well, of 3 students of Tian or Zhang. I don't remember now the names, and I am out of time. Where there's a similar problems or the same speed for hyperbolic system. We are much more interested in the case of non-hyperbolic system. And then you take this number, okay? Well, this is a theorem with Gelfer, Rams, Isan. You take this number, and then for every epsilon bigger than 0, there is an arc of ergodic method. Okay, and this arc has two properties. You have that this method all have Lyapunov exponent 0. The method, this number is continuous, but this is essentially a consequence of the Katok-Feldman property, but we need to work on this. And also, well, we have that the entropy of the first method is 0, and the entropy of the last method is bigger than this number minus epsilon. Okay? And as a consequence, we also got the variational principle holds for L naught, or for no hyperbolic method. You decide what you want to provide. That is, you fix any epsilon close to 0, and then we construct a sequence of ergodic method that started in 0 and finished arbitrarily close to L0, to the entropy minus epsilon. And then, well, I have no time, then I cannot give ideas of the proof. I am the last plenary speaker of this week, and Alejandro cannot thank the organizer because he's an organizer and he's a very modest person. And then it's my duty to thank the organizer, please. Well, they will have more next week, I hope. It's also time to thank the speaker of the mini course, please. And then, well, let me go to the figure, to the photo, and then you can participate in this contest. You can identify the people that identify more. Yesterday with Alberto, we identify about, where is Alberto? Is not here. Well, we identify about 15 people. 15, but you are very old people, you know. So Stefano is there. Okay, I'm going to stop here. Thank you for the attention. Sorry? Coxar is not, but for instance, surprisingly, it says there. You can see Stefano, Marco Brunella, but you know, you need to participate because I cannot put here the biscotti and also you can do question about my talk. Eh?
Okay, yes.
I am self-boycotting my talk. Terrible. This is a trick to avoid questions, you know. Well, you have, I have this for the winner, but it's, I don't know how to decide this.
What year was this?
Sorry?
Year.
92. 92. Stefano is in the middle. You can see Stefano there.
I cannot see myself.
Okay, you are, you. Sealves is there, Renato Turriaga, I guess that Marco Martens. That is Canning. My God. Sorry, well, it's Sergio Plaza, Gian Christophe, Sinai, Dacoz is there, Alberto.
Was the secretary.
Hiroki Kokubo. Well, many people. Pedro Mendes. What's I say? I will give you the cookies and you give somebody. No, but you need to.
We have to chat.
You say.
Just one word that picture we. I took it off.
Well.
Okay, so let's